All right, welcome back to Chemistry 2312, Organic Chemistry. Good morning, afternoon, or evening, depending on when you're watching this. Uh, First, let's go over some of the news and updates for the class. If you are not already aware, hopefully you are. There have been a number of changes in the format, and you can go to Canvas to see these updates in two primary documents, the general updates for 2312 and the grade scope submission guide. Problem set 12, this will be due on Wednesday before class. So this will be submitted to Gradescope following the instructions, and hopefully you all have had some practice at doing that and streamlining the process. To go over the last lecture, lecture 26, that's posted on YouTube, we pretty much did all of topic 6. It was reduced in content, and it's all about amines. So we had learned some amine synthesis earlier in the carboxylic acid section. This kind of rounds out some more of the ways to make amines and different reactions that they do. We talked about acid-base chemistry, how to predict how acidic or basic something is. This utilized a lot of those ideas we introduced actually early on in topic 1. Talked about how amines are nucleophilic, and you can alkylate them with alkyl halides, but this is pretty hard to control the number of alkylation events that take place, so it's not always the most effective way to synthesize these molecules. So then we learned a few other strategies to selectively make things like primary amines or secondary amines. The most useful ways of making primary amines that we learned in this section would be the Gabriel synthesis, where we use the phthalimide anion to displace and then essentially remove all of the phthalimide group with hydrazine. We also learned two new reactions. That's reduction of azides. This can be done with either lithium aluminum hydride or platinum oxide and hydrogen gas. And we also learned how we could reduce oximes selectively to primary amines using dissolving metal conditions of sodium and ethanol. Now to make secondary and tertiary amines, the preferred method is reductive amination, and we had a new reagent that came on the scene, sodium cyanoborohydride, that's even less reactive than sodium borohydride. It's very selective in its reactivity, and it only reacts with positively charged iminium groups. So it really needs to have this positive charge to react with something. It's fairly stable to things like acid, and we frequently will add in catalytic acetic acid to these reactions to both catalyze the formation of these iminiums and get them to go forward. And whether you start with a primary amine or a secondary amine will determine whether you make a secondary or tertiary amine product. In the last section, we talked about the Curtius rearrangement, which I said I liked a lot. It's because it's pretty wild. We turned an acid chloride into an isocyanate. So we end up losing this carbon, and it gets sort of migrated over one with now making formation of a carbon-nitrogen bond. It goes through acyl azide intermediates with a key arrow step shown here, where we can have nitrogen gas as a good leaving group that happens alongside a 1,2 shift that forms the isocyanate. And this becomes relevant for the amine section because you can add water to the isocyanates and you would get out primary amines afterwards. And of course, this isocyanate could be isolated and then used for other addition reactions to make things like carbamates or ureas. So now we're going to start a new topic. This is topic 7. This is going to be focusing on enol and enolate chemistry. Note that this is not on exam 4. This is not on exam 4. So this is some material that we'll start covering now, just so that we'll have enough material to have a decent amount of material for exam 5 later on. So we're going to get started. This still focuses around carbonyl compounds. So we're going to learn some different reactions that they can do. Most of what we've looked at earlier in topics, 3, 4, 5, 6, are these sorts of addition reactions to carbonyls where we see that they are good electrophiles, where nucleophiles can go and add in to the polarized carbon-oxygen double bond, and then after workup we get different sorts of addition products. Or additionally, we have these sorts of addition-elimination products that can form through substitution reactions when we have good leaving groups on the carbonyl. So this section is looking at ways of actually using carbonyls as nucleophiles. And that sounds maybe a bit counterintuitive since we keep focusing on how these are always electrophiles when we've seen them so far. And in order to turn these into good nucleophiles, we usually need to do something to them first. We need to have a reaction take place. We're going to see how we can do this with either bases or acids. But first we're going to focus here on just what an enolate is and how it can form using basic reagents. So we have B here as just your general generic base. And these alpha hydrogens that are next door to the carbonyls also become quite acidic. So we can see here that the alpha hydrogens are usually a pKa of about 19 or 20. So even though they are a CH bond, they are much, much more acidic than normal CH bonds that are in the 40 to 50 range. So if you just go one carbon over, there's a dramatic increase in pKa, where these are effectively not acidic at all. But if we add the appropriate base, we can see why these are relatively acidic. It's because if we deprotonate this hydrogen, we can make an enolate, and this enolate has a resonance structure where we can put this negative charge on the oxygen. So this explains the peculiar acidity of these CH bonds, because really the conjugate base is well stabilized, both by resonance and by putting the negative charge on a more electronegative atom. And these end up being nucleophiles now because they are negatively charged. And these are called enolates. So these are going to be some of the major species that we'll be using in class. We're going to learn how they react, where they react, and all of these great things soon. So one of the basic reactions you can have actually is just the reversible protonation and deprotonation of a carbonyl compound that has acidic hydrogens. Acidic hydrogens means there is a proton alpha to the carbonyl. So in this case, we can have something like hydroxide. So if you remember, the pKa of water is around 16, and we just said on this previous slide that these alpha hydrogen are 19 or 20, we will be able to say that probably this equilibrium will still end up favoring the keto form. But because this is in a reasonable pKa range between the two, we will have an equilibrium where we'll start to make small amounts of these enolates, or whether this negative charge is on the carbon, or you can draw the negative charge on the oxygen. So along the way, you see there's actually two different reactive forms of the enolate. So we can imagine this lone pair on the carbon reacting directly, or we could imagine the lone pair on the oxygen and the other resonance structure also reacting with water. So we know that acid-base reactions usually go back and forth. So we can end up having the hydrogen being taken by the carbon, and we get the exact same product back. This is the keto form. But alternatively, you could also get protonation at the oxygen to give us the enol form. And so the enol form is completely different than what we would expect in terms of reactivity to the keto form. Whereas the keto form is inherently electrophilic because of the strong carbon-oxygen bond and its polarization, the enol form actually becomes nucleophilic. And so you may be thinking about this. So you can make some analogy to the section we had in topic 2 when we did electrophilic aromatic substitution, where the lone pairs on this oxygen were strong electron donating groups and were ortho para activators. So the lone pair here was able to donate down and attack things at either the ortho or para positions. In a similar way, we're going to see how enols are very similar in the same way that they have this lone pair that is able to donate electron density into this double bond and make this carbon more nucleophilic. So we talked about how we could have this take place under basic conditions through a deprotonation reprotonation strategy. You can also have acid catalyzed tautomerization. So similar to the acid versus basic conditions that we've seen in the past, um, this will have the overall same net effect, but we're going to need to proceed through slightly different mechanisms because now we're not going to involve any deprotonation of the CH bond. First, we'll go through protonation of the carbonyl. After we protonate this carbonyl, we end up with this oxocarbenium intermediate. We know this is very electrophilic, which means that this is also very acidic. So both the CH bond, both of the hydrogen on this oxygen becomes more acidic, and also the hydrogen on this carbon becomes more acidic, because both of them will lead to neutral compounds. So if we have our water molecule come back, this would be our base in this reaction, and it simply took the hydrogen away from the oxygen. We would get our keto form back, whereas now we have another option of where the water molecule could also deprotonate the carbon CH bond, and it will now lead us to the enol form. So we see we have access to the keto and enol forms actually under both acidic and basic conditions. And as we saw before, we have the exact same keto and enol forms where the enol form now is going to be quite a nucleophilic double bond. It's not going to be as strong as a nucleophile as something like an amine, but it's still much more nucleophilic than your average double bond. So when we look at keto-enol equilibria, and this again can happen under acid or basic conditions, it's important to think about the thermodynamics of this. So it still is never going to be likely favoring the enol form unless there's other additional benefits to being in the enol form, either through resonance or something like formation of aromaticity. So we're just going to go through a couple different examples to highlight, approximately how much of each of these keto-enol tautomers are present in solution to kind of get an idea of where they are overall energetically. So if we look at something like acetaldehyde, this is approximately 100% in the keto form. So even though we are able to make small amounts of this enol form, and it might be able to do some reactions along the way, it is virtually not there at all. If we go to something like acetone, this exists in more than 99% in the keto form. So again, this strongly favors being in the keto form. This ends up being 1.5 times 10 to the negative fourth percent. So virtually none of it's there. So we'll see reactions where we're able to generate small amounts of this during the reactions, and it can be a reactive species, but it's never going to be an isolable intermediate. Excuse me. Once you go to cyclic systems, now we start to see maybe a tiny bit more. So a cyclohexanone goes to 98%, where now we have 1.2% of the enol form, but still effectively none is present in solution. Things start to change a bit once we get to these 1,3 diketone systems. So this is a pentane dione. Now actually the enol form will be favored. The keto form is 24%, whereas the enol form is 76%. So the reason behind this is that now we have a couple extra factors. One is we have hydrogen bonding that is present. That'll make this isomer slightly more stable. And we also have the combination of resonance, where lone pairs from this oxygen can also be donating into this carbonyl. And if they donate all the way, this hydrogen can transfer. So we also have increased resonance. So it's kind of like putting an electron-rich double bond right next to an electron withdrawing carbonyl. These push-pull systems end up being quite stabilizing. And the most extreme example is with something like phenol. So while we always draw phenol in this form draw here, this is formally its enol form. And we've always seen it in this form, so it's probably not surprising that this is, in fact, 100% in the enol form. And then, of course, here we have a couple different factors. The main one is the gain of aromaticity. And you could just say generally resonance in general, because now we end up having a double bond that is conjugated much more. So on the whole, when we see carbonyl compounds, simple aldehydes and ketones will be dominantly in the keto form, whereas once we get to things like 1,3-diketones or 1,3-keto esters, which we'll learn about later in this topic, we will have an appreciable amount of the enol around. And for things that are aromatic, they will just stay in their enol form.